Okay, we will go through the exemplar problems in class 12 physics, chapter 2, electrostatic potential and capacitance. Okay, before going through it, I will show you some general information. When we bring a test charge from infinity towards a charge q, you have to apply a external force because these positive charges repel each other. You have to apply external force. That force is stored as potential energy. When you move closer to this charge, the potential energy increases. At the same time, kinetic energy decreases. Okay. So now when you release the charge, then charge will move across the field direction, electric field direction. Now in this direction, the potential energy will decrease, kinetic energy will increase. Okay, now when you bring the charge, potential energy will increase. That is, this external force you have to apply more, that is stored as potential energy. Kinetic energy will decrease, but when you release the charge will move towards this direction, electric field direction, potential energy will decrease, kinetic energy will increase. But both are conserved. That means at any point, the potential energy is kinetic energy, potential plus kinetic energy is constant. Okay, either in this direction or in this direction. This direction potential energy increases means this direction potential energy decreases. When you add both the energy, that will be constant. Okay, that is conserved. That is potential energy plus kinetic energy when you forward and potential reverse at any point is same. Okay, work done in bringing a charge q to a point where the voltage is V, potential is V is QV. Okay, work done is QV. Potential at this point, Q is the state charge. Okay, work done by the external force is negative of the work done by the electrical force. Work done by the electrical force. Okay, work done by the external force is negative of the work done by the electrical force. Okay, a capacitor is connected like this as shown in the figure. The internal resistance they are given. The amount of charge on the capacitor will be. Okay, whenever you connect a capacitor, immediately it will be like a short circuit. Okay, but when it is fully charged, that it will be open. There will not be any current flow in this direction. Okay. See, this is only connected when at that time current will flow. After it is fully charged, it will act like a open. That means there will not be current through this capacitor, this circuit. Okay, now the resist here 2.5 volt. The current will flow here only. This circuit, and we have 2.5 volt, and this 2.5 ohm as a resistance. So current is 2.5 volt. We have this 0.5 is the internal resistance they are given. So voltage by resistance 1 ampere current will flow. Okay. Here this circuit is open. So now the charge across the capacitor between these 2 points is the voltage between these 2 points. That is the voltage here also. No current will flow. So there is 2 volt here between A and B. So 2 charge equal to capacitance into voltage. Capacitance 4 microfarad, 2 volt is 8 microfarad is the answer. The positively charged particle is released from the rest in an uniform electric field. Okay, uniform electric field. Electric potential energy of the charge, as I already told you, it decreases because the charge moves along the electric field. When it moves along the electric, potential energy decreases, kinetic energy only will increase. Okay, here we are asking potential energy. Here we shows the equipotential distributed in space. A charged object is moved from point A to B. So here you have to see the work done and depends only on the initial and final potential, not on the path. Okay, so here also 20 volt to 10 volt. Okay, here also 20 volt to 10 volt, point A to B. Everywhere 20 volt to 10 volt. They are moving from 20 volt to 10 volt. Okay, so the work done will be same. Okay, it means that the work done by an electric field moving a charge from one point to another depends only on the initial and final points. Okay, so that means in all the cases the work done in all cases will be same. Electrostatic potential on the surface of the charge conductor is 100 volt. Two statements are made from this. At any point inside the sphere, the charge electric intensity is 0. That is, electric field is 0. At any point inside this where the electrostatic potential is okay. This is true. This is also true. Yes, one it is because the inside there is EQ potential. Okay, potential inside and on the surface of a charged conductor is same. Okay, EQ potential. So that is EQ potential, and the electric field, electric intensity, strength of the electric field, because electric field inside the conductor is 0, strength also 0. EQ potential at a distance from the collection of charges, the total sum of the is not 0, approximately. Okay, the potential is same at from the equation, potential is same at a distance. E equal to Q by 4 by epsilon naught R. It depends on the distance. So equidistance from that charge, we will have the equipotential 4. See here, it depends only on the charge, on the distance. Okay, so equal distance will have the equipotential. Okay, a parallel plate capacitor is made up of two dielectric flux in series. Okay, one of the flux thickness is this dielectric constant, and the other is thickness is the dielectric constant as shown in figure. This arrangement can be thought of a dielectric slab of a single slab with this thickness, and they are asking the dielectric constant. So here we are treat like capacitance is connected in series. So when you have a dielectric, the capacitance will decrease. Book page 26. So here this is the capacitance due to dielectric. We have a dielectric constant. This is permittivity of the medium, of the dielectric medium, area of cross section, d distance. Okay, here this formula, then we have to use the, when we connect capacitors in series, when we connect capacitors in series, so this is the final capacitance is 1 by C1 plus 1 by C2. This is the resultant capacitance, that is C1 C2 divided by C1 plus C2 divided by C1 plus C2. Okay, this is the resultant capacitance when you connect in series, that is the C equal to C1 C2, resultant C equal to C1 C2 divided by C1 plus C2. Actually not 1 by C equal to, actually C equal to, connected in series. Okay, now you have to apply that formula with the dielectric C1 C2 C1 plus C2. So when you simplify, you will get this. Okay, K1 D2 plus K2 D1. Okay, actually here this is a K1 D2, K2 D1 should be there. Okay, there's some printing mistake. Okay, this is the answer. Consider a uniform electric field in the direction. The potential is constant. This is the potential decreases on the distance, the direction of the electric field. Okay, so now we have 10. See here, for a uniform electric field, say along x-axis, the equipotential surface is on the other two planes, okay, on the same distance. So here same thing is applied when it is a z plane. So the xy planes will have the equipotential for given z. Equipotential surfaces are closer in the regions of the large electric field, be more crowded on the surface. Okay, these things all are true. Work done to move a charge along the equipotential from A to B, electric field into distance. Okay, so equipotential means work done will be 0 because the potential is difference is same. The region of the constant electric field, potential electric field will be 0 because we have to differentiate dV by dt. There can be no charge inside the region. Okay, 2.11. Circuit shown below initially key 1 is closed and gate is open, then K1 is open, K2 is closed. Okay, now when this is closed and this will get charged. Now it is open, this charge will this is closed, this charge will get distributed here also. Charge conservation, this is total charge will be distributed between these two capacitors. Okay, and they are in parallel, so this voltage is same as this voltage, so the total charge will be distributed between these two. Law of conservation of charges. Okay, total charge on the capacitor C1 plus charge on the capacitor C2. Since this voltage is same, Q equal to CV. Okay, this charge will be distributed between this and this. Charge on C1 gets redistributed. Okay, such that this voltage is same. Total charge is conserved. Total charge is charge on this capacitor and the charge on this capacitor. Okay. Okay, the similar thing is given here. Connecting two capacitors. Okay, how the charge distribution takes place. If a conductor has a potential which is not equal to 0, there are no charges anywhere else outside, then there must be charges on the surface or inside. There may be cavity and inside that cavity charge may be there. There cannot be any charge the body of the conductor. A parallel plate capacitor is connected to a battery. Okay, shown here. Initially its key is kept closed and the plate of capacitor are moved but using the insulating handle. Then the key is opened and the plates of the capacitors are moved apart using. Okay, So initially when the key is closed and the place of the capacitance key is closed means this will get charged. Okay, this capacitor will charge. So V remains same and Q changes. Okay, when the key is opened, then charge conservation, charge remains same and voltage changes. Consider two conducting spheres R1 and R2. R1 is greater than R2, radius of first conducting sphere. If two are the same potential, that is important. Okay, same potential, that means Q equal to V equal to Q by 4 power not R. Okay, same potential and the radius of R1 is greater than the larger sphere has the same charge, have the more charge than the smaller sphere. Okay, state whether the charge density of the smaller sphere is more than that of the larger sphere. Okay, so here we have to use the potential formula. Both are having the same potential. Okay, this is the potential formula, Q by R. Okay, charge. This is Q1 charge on the R1 and this is the R2. R1 is greater than the R2. Okay, now both are equal. Now this charge density into R1 equal charge. So now if you see the ratio of the charge densities, so from this ratio, since R1 is greater than R2, so the charge density on the smaller sphere, that is R2, is greater than the R1. Smaller sphere, okay, that is charge density on the smaller sphere is greater than the large sphere. Do free electrons travel to the region of the higher potential, or these will travel towards the higher potential, that is positive charge? Can there be a potential difference between two adjacent conductors carrying the same charge? 2.16. Okay, this is 2.16. Yes, if the sizes are different. Okay, if the sizes of the conductor are different. Okay, what is the potential difference between the two conductors? The sizes are different, then potential will be different. Can the potential function have a maximum or minimum in the free phase? Free phase, there is no charge, there is no maximum, minimum. Okay, a test charge is Q is inside the is made to move the electric field of a point charge Q along the two different closed paths. Okay, these are the two different paths. See here, what we have to know is, because this work done depends on the initial and final point. So this is a closed path. If both points are same, the work done is 0. Okay, 18. As the electric field is conducted, work done will be 0 in both the cases. See here, work done depends on initial and final. So initial and final points are same. The work done is 0. Prove that the closely equipotent surface with no charge within itself must enclose an equipotential volume. 2.19. Okay, you can go through this answer. A capacitor has some dielectric between its place, okay, and the capacitor is connected to a DC, so the battery is now disconnected, and then dielectric is removed. Dielectric removed means capacitance will decrease. State whether the capacitance, the energy stored, electric field charge or increase decrease, okay. 20. Q equal to CV, okay. After battery is disconnected, the charge will be conserved, charge will be same, but after disconnection the capacitor will decrease, okay. Capacitance will decrease. So when capacitance decrease but charge has to be maintained the same, that means voltage has to be increased, okay. Q will be same, so capacitance will decrease, that means voltage has to be increased, okay. Voltage will increase. Energy equal to half CV square, C equal to Q by V, C equal to Q by V, after that and Q square by 2C, okay. So when capacitance is decreased, that means this is in denominator, the energy stored will increase, okay. Okay. Prove that if an insulated uncharged conductor is placed near a charged conductor and no other conductors are present, the charged body is intermediate between 2.21. Okay, this is the answer. So you can go through this answer. Calculate the potential energy of the point charge along the axis due to positive uniformly distributed along the ring of radius, or sketch the potential energy as a function of the distance from this, okay. 2.22. So okay, this is the equation, variation of potential energy, okay. 2.23 also this same formula, 23, okay. So you can for this also you can go through the answer. 2 point charges are placed, okay, on the one axis respectively. Find the equation by the equipotential surface. If these two are in one plane, then equipotential surface will be in the other two planes. So this is in 10, 25. Equipotential surfaces, okay, is here they are given. So it is in one axis, the equipotential will be in the other axis. Here x axis and y z is equipotential for the same distance. So you can go through the answers for all this thing. Two metal spheres are and the two are with these same surface charge density, okay. Charge density is same. They brought in contact means their voltage will be same, that means there will be some charge transfer, okay. And they are in contact, that means their potential will be same in both the conductors. And separated, now the surface charge density, though when the potential is same, that means the smaller radius will have the more surface charge density than the small will have the more charge density. Before contact, okay. So here you can go to the smaller will have the more charge. Here see, this is smaller, here means smaller will have the more charge density. So these things you can go through the answers, okay.